little thought exercise. For those of you that had me in Chem 109, this might look familiar. It's the exact same thought exercise I asked you to do when you were in general chemistry. But it's still just as tried and true as ever. So I'm going to set you up this thought experiment, and I want you to pause the video and just think for a moment what these two answers should be. Okay, so suppose we have a container, and it's exactly 22.42 liters. We've put 273.15 Kelvin in this container. Don't worry about this container with H2O. Let's just focus on this container with helium for now, okay? And we put 1 mole of helium atoms. So we have a container. We put 1 mole of helium atoms. It's 22.42 liters and it's 273.15 Kelvin. What is the observed pressure in this container? Okay? Is it, and I'll give you some ranges, okay? We'll just say, is it 1 ATM? Is it greater than 1 ATM? Or is it less than 1 ATM? Okay, so think about what that is for this case of helium. Now, then let's talk about this other one. So we have the same container, 22.42 liters. We put 1 mole of water molecules in there, and it's 273.15 Kelvin. Now, I know you're chemists, and you're like, but it's gonna condense. And you'd be right. Let's just ignore that for now, okay? Don't worry about the water condensing. Maybe we could say it's 273.17 Kelvin or something, okay? So don't worry about condensation. What's the observed pressure here? Is it exactly 1? Is it greater than 1? Or is it less than 1 atmosphere? Okay? So I want you to actually pause the video and think about that for a moment, okay? Okay, hopefully you paused. Hopefully you thought about it for a minute. I'm not going to pause. I'm going to keep going, okay? As it turns out, to 4 significant digits. I got 4 sig figs right here in the volume, okay? It would be 1.000, right? And hopefully you remember, we could calculate that even too, right? P equals nRT over V, okay? And we would get 1.000 if we were to calculate that. And of course, over here, we would get the exact same number because it's the same equation. However, what this equation of state is not accounting for is the fact that molecules interact and that they occupy volume. Okay, so we're going to get to that in a few more slides. I'm going to highlight the differences between the ideal gas and the real gas, right? But if you notice on this water, I've got here these oxygens pointing towards the hydrogens, right? Because there's going to be some intermolecular forces at play, right? You all know that. We love water and hydrogen bonding and all its capabilities. And so what this would actually do is make this pressure just a little less. I'm going to change that equal sign, and I'm going to make it a less than sign. It would be just a little bit less than 1.0. Okay, I won't put any sig figs on there yet, but we'll just say it will be a little bit less than 1.0. And that is because the observed pressure is a result of the gases colliding with the container walls, right? These water molecules are going to have a greater affinity for each other. They're going to suck each other in from the container, and the observed pressure would actually be just a little less than 1 ATM. Okay, so how do we start to build that up? Okay, well, we can start to correct for what the ideal pressure should be by saying, well, this ideal pressure is going to be this observed pressure plus this whole chunk right here, okay, represents what I'm going to call a collisional term. And those of you that are remember your Gen Chem days, you'll recognize that this is part of the van der Waal equation, and I'm going to put that together in total. But specifically, this chunk, A times N over V squared, gives us this collisional term. It accounts for the fact that these molecules are interacting with each other, And that influences them to suck into each other and collide with each other more and collide with the container walls less. Okay, these molecules are attracting each other in. And the size and magnitude of this A term gives us that effect. So for example, you notice helium, it does have a definite A term. It has a value for this collisional term, 0.0341 liters squared per mole squared. Okay? And if I plug in 1, and I should have put in sig figs, right? When you calculate this, you do get 1.000. I meant to indicate that on all these 1.0s, okay? You do, in fact, get 1.000 when you consider this 1 mole of gas. So, right, this is 1 mole of gas at 273.15 Kelvin. The ideal pressure we know is 1 for those conditions at STP, right? But the observed pressure would also be very close to 1. Same with neon. It actually doesn't change it all that much. But now, look, once you jump up to argon, argon's A term goes up almost a full power of 10, and now it starts to become noticeable. And we get all the way down to water, 5.46, one of the largest values. Chlorine's value is actually bigger. Gives you a pretty noticeable effect, 0.989 if you had a very sensitive pressure meter. Okay. And so what you might guess is at play here are the intermolecular forces. So for example, we know water and ammonia are capable of hydrogen bonding, right? Okay, so that's a very strong intermolecular force. As a result, they have a pretty large A value. So what's the deal with chlorine? Okay, well, as it turns out, chlorine has quite strong London dispersion forces because of that mess of electrons surrounding it, right? So those electrons can undergo instantaneous induced dipole in the vicinity of neighboring chlorines, right? And you notice here what happens with this collisional term, the more number of moles you have, the bigger the effect is going to be, right? Conversely, the more volume you have, the smaller effect this is going to be. So as you force these molecules to get closer and closer together by either making more of them, by putting more of them in a container, or shrinking the size of the container, they will have no choice but to get close to each other, start to interact, attract each other, and reduce their collisions with the outside container, thereby reducing the observed pressure. Okay? So also, another pillar of ideal gas that I'll summarize here momentarily. Okay? The ideal gas law does not account for the volume of the molecules themselves. Okay? So as it turns out, the molecules do in fact have volume. They have finite volume. And that's given by the B term. And if you look at these units, liter per mole, this would actually be, so if you took helium and you condensed 1 mole of helium, it would actually occupy 0.0237 liters. So that's 23.7 milliliters if you could condense a mole of helium. That's not accounting for the space between the heliums, but just condensing them all together. All right? And so then, right, if we know that the ideal volume is 22.42 liters in 1 mole, then we can correct for that ideal volume with this observed volume, all right? And so you notice in all of the observed volumes, they're just slightly bigger than the ideal volume, right? Because the molecules themselves are taking up space, okay? And so that's what that B term gives us. And it's kind of hard to distinguish a trend here with these molecules, but certainly if you go through the noble gases, you can see the periodic trend almost perfectly. Helium actually occupies more space than neon, and that's actually due to neon's nucleus, right? It has more protons in it, and it can suck in those electrons just a little bit tighter. But then now when we get up to argon or even krypton or xenon, you can see that those, the atoms are getting bigger, right? So they occupy more volume, okay? And then certainly like chlorine is fairly large at 0.0562. Water, surprisingly, is pretty small because water can actually cram together quite efficiently, okay?